All right, now we are in business. All right, so we were talking about capillary rise, and it all has to do. Okay, I'm just going to leave that alone. I'm going to break the keyboard up here if I'm not careful. Hold on. No, it just made it worse. Okay, that's fine. Okay, actually, no, this is a problem. Hold on. There we go. Okay. All right. Anyway, CO2 does not wet most geological materials. Mainly when you look at the type of rocks that you're injecting it into, like in a saline aquifer, those are typically going to be sandstones. And that fact causes some interesting things to happen when you inject it into a rock. And it has to do with the interfacial phenomena at the contact between the CO2 and the water, but also where that contact intersects with the solid grains. So there's some interesting things that happen. So, we've all seen this experiment with the capillary rise experiment, where if you put a glass tube into a dish of water, the water will climb up the inside of the tube to some equilibrium height that is inversely proportional to the diameter of the tube. And this happens because of these two properties called interfacial tension and wettability. Interfacial tension is this force that exists in the plane of an interface between two immiscible fluids. Like air and water, gas and water, that sort of thing. And it happens because I think, we talked about this on Friday, but the molecules that are in this one phase here, they're all, balanced and at equilibrium with the intermolecular forces between them and their neighbors. But at the interface, you don't have neighboring molecules up here in the other phase. And so to retain the shape of that interface, you have to have a force acting in the plane of that interface that holds everything together. And there's a property that we can get if we consider the work done on changing the area of that interface. So if everything is constant, so pressure, volume, temperature, entropy, if we hold all that constant, the increment of the internal energy of this system, so this goes back to the first law of thermodynamics, it's going to be equal to the opposite of the increment of work that you do to the system. Okay. And we can write an equivalent expression where we define interfacial work as the change in area times this property called the interfacial tension, which has units of, it's either energy per unit area or force per unit length. But that's the interfacial tension. And it tells us that if we change the area of that interface by some amount dA, the internal energy of the system will change by du, and they're related by the interfacial tension. Now, to minimize any energy changes, we need to minimize the changes in the area of the system. And the shape that has the smallest surface area to volume ratio is going to be a sphere. And so the interface between two immiscible fluids will always form either an entire sphere, in the case of like a bubble or a droplet, or at least part of a sphere. And that allows it to minimize the area. So that's why we get this curved meniscus in here, because it's trying to minimize the area of that interface. Okay, so if we have this curved interface here, there's actually an interesting thing that happens. So if we imagine, let's think of a bubble of gas that's immersed in water. So I haven't specified what this gas is. It's green, but that's all we know about it. It doesn't really matter what the composition is. Now, if the total volume, the temperature of the system are held constant, when I say system, that's going to be the bubble of gas and its surrounding water, okay? We can define a property called the Helmholtz free energy, and that's simply obtained by taking the total internal energy and subtracting T times S, so temperature, and then S is entropy. And that gives us what's called the Helmholtz free energy. Now, there's going to be two types of work that can happen here. We can do interfacial work because we have this interface, and then we can also do PV work. So if we keep temperature and entropy the same, then the only things that are going to change the internal energy are the PV work and the interfacial work. So we can write that the increment of Helmholtz free energy is the sum of the increment of PV work that's done and the increment of interfacial work. And we just saw how to define interfacial work. It has to do with the area of that interface and the interfacial tension. Now, so that's defined. The PV work is, if you think about increasing the volume of the bubble, you're going to have to push some of the water out of the way. Again, remembering that the total system has a constant volume. So you're going to increase the volume of the bubble and compress the water. So that's the work that you're doing. And that incremental work, if we think about the change in the volume of the bubble, so that's the dV that we're looking at here. So the work is being done by the bubble, so the pressure in the bubble is positive. And then we're doing work on the water, so that water phase pressure is subtracted. And we can re-express this in this term here. So that's just the two components of that, the PV work that we have to think about. And then remember, we defined the interfacial work associated with changing the area of that interface with the bubble expanding. That's just given by this term here. So the total change in the Helmholtz free energy is this expression here, where again, the first part, that's the PV work. And then the second part is the interfacial work. All right, so we can actually write expressions for this now. If we are simply increasing or just changing the bubble radius to a new value, which we'll call R1, then the dV is simply going to be given by this term here. So that's the incremental change in the volume of the sphere. And then the incremental change in the area of the interface is going to be given by this expression here. Okay. And so what this allows us to do, if we plug that into the Helmholtz free energy, we end up with a differential equation. So the change in Helmholtz free energy with the change in the radius of the sphere is just given by this term over here. And if we minimize the Helmholtz free energy, which is what we always want to do, this derivative here has to be equal to 0. So this term has to be equal to that term. And if we do the algebraic manipulation here, we see that the bubble and the water phase pressure are not going to be the same. They're going to differ from each other by amount equal to 2 sigma over R1. And so what this tells us is just due to the fact that we have to minimize the energy by changing the interfacial area, we always have a pressure discontinuity across the interface between the bubble and the water, where the pressure inside the bubble is always larger. Okay. So this is an important point for understanding the behavior of multiple fluid phases in porous media, that their pressures are actually going to be different from each other. And this is really essential for understanding how you trap CO2 beneath a capillary seal, which we'll get to in a little bit. Okay, so we see here now that in this bubble, the interior pressure is going to be lower, excuse me, got that wrong. The interior pressure is going to be higher than the exterior pressure. And those of you who either are taking or have taken my petrophysics class know that one of the things I always talk about is that when you move from the convex side of an interface to the concave side of the interface, the pressure goes up. You have an instantaneous jump in pressure when you cross that interface. So if we go back to our capillary tubes, what that means is that at the bottom of this tube, where we've got the contact between the air and the bulk water phase, there's the pressure in both phases is roughly equal to each other. It's 1 atmosphere in both cases. Okay, now I'm going to back up for a second. You might, if you've been paying attention, you might be thinking, but wait a minute, Dr. Daigle, didn't you say that interface always has to form part of the surface of a sphere? And I did say that. But here's the deal. When you have a very large interface, like if you think of I don't know, a Petri dish or something, and you've poured water in it, the surface of that air-water contact is going to be part of a sphere, okay? But it's just going to be part of a really, really big sphere, such that the curvature is really not observable to the naked eye. And what that means is that there's going to be a negligible pressure difference across that interface. So basically, we can say that at this point right here, the air and the water pressure are equal to each other, and they're both 1 atmosphere. Okay, now at the top of the water column, the air pressure outside, just above that meniscus, is going to be 1 atmosphere. If we assume that this height is not very large, such that there's a negligible difference in air pressure between the top and the bottom. But because we have this curved interface here, if I go from the concave side of that to the convex side, this is the opposite of the little aphorism that I just told you, the pressure has to drop. So at the top of the water column, the water phase pressure is actually less than 1 atmosphere. And that means that there's a gradient in pressure that goes down through that water column, which is one interesting thing. But for that water column to be sitting there in the tube and have been pulled up there, something has to be holding it up, okay? And so the question is, what is actually holding it up? So that's the other part of what we're talking about here, which is the wettability component. So if I zoom in to this contact line here where it intersects the glass, you can see that it intersects it with an angle, and we call that the contact angle. The closer that contact angle is to 0, the more wetting the water is on that surface. If it's generally, we say if it's less than 60 degrees, then we call that a water wet surface. If it's greater than 120 degrees, we say it's not a water wet surface. It's wetting to some other fluid. And we can have intermediate wetting where it's somewhere in between those. A lot of surfaces that we experience in our day-to-day life are actually designed to be mildly hydrophobic, so they're not water wetting, and that allows water to bead up and run off and not soak in. So just kind of an interesting side note there. The contact angle is really just the macroscopic approximation of a bunch of processes that or forces that exist at the molecular scale. So it really has to do with the balance of electrostatic forces, van der Waals forces, solvation forces, and other things that cause the water to be attracted or repelled from this solid substrate. So you can get really into the weeds on this, and it's actually a really fascinating area to get into, actually what gives rise to this phenomenon of wettability. But all you really need to worry about right now is this contact angle. Down here, this is a couple of images. This is water on glass, which you can see it's clearly wetting, because that if we draw a contact angle like that, it's going to be less than 60 degrees, so that's wetting. But here's a water drop sitting on a plant leaf. It's a lotus leaf, and you can see that this lotus leaf is naturally hydrophobic, and so the water forms this bead here. Okay, so that's wettability. And what happens with the interface is that there's an interfacial force acting in the plane of the air-water interface, right? We know that. And that has a component that acts vertically, and so it counteracts gravity. And that means that the water will climb up the surface of the glass until it gets to a height where the capillary force balances the gravitational force, which is due to the weight of this water column. So that's what causes capillary rise. And the difference across this interface is going to be given by this equation here. It's a little bit different than the one we derived for using the Helmholtz free energy. And the reason for that is that the radius that we're using here is not the radius of curvature of this interface. It's actually the radius of the tube. So that's why we have to throw in the cosine of theta. Incidentally, this is known as Washburn's equation. It's the capillary pressure across an interface in a tube, a cylindrical capillary tube. Okay, so that was a lot of information. I hope it was mainly reviewed for most of y'all, but I'll pause here and I'll take any questions, if there are. Fantastic. Okay. So you're probably asking yourself, what does this have to do with CO2 injection? And let's talk about what it does. All right, so let's imagine I took my capillary tube setup and I turned it on its side. So we're not going to worry about gravity right now. But let's imagine I've got 3 glass capillary tubes. They're filled with water, and they each have a different radius. And they are connected to a large reservoir of carbon dioxide. So because these tubes are made of glass, water is going to be the wetting phase, and CO2 is not going to be the wetting phase. Okay, so we know that if you push a little bit of CO2 into any one of these tubes, you'll form a CO2 water interface, which will have some curvature to it because CO2 is not wetting, and there will be a pressure discontinuity across that. And we know that the magnitude of that pressure difference is going to be given by Washburn's equation here. So let's think about it. If I start ramping up the pressure in this CO2 reservoir, which tube is it going to go into first? The smallest. Why the smallest? Well, the way to think about this actually is that, so at equilibrium here, we're starting off, the CO2 and the water pressure are exactly equal to each other. So if I start increasing the CO2 pressure, if I have a small difference between the CO2 pressure and the water phase pressure, that would be a small capillary pressure, right? And so the CO2 water interface would have the smallest capillary pressure across it in which tube? The smallest or the biggest? Going to be the biggest, right? Because Washburn's equation tells us that that pressure difference is going to be inversely proportional to the radius of that tube. So what we see is we will preferentially go into the larger or the largest pore first, because you can form that interface at the lowest pressure. We haven't gotten up to a pressure where we can form an interface within these tubes. Okay, now what we're doing here is a process called drainage, which is where we are displacing the wetting fluid with a non-wetting fluid. And so you could think of this being directly analogous to injecting carbon dioxide into a saline aquifer. When you do that process, you have to overcome the capillary pressure barrier in the pores. And the higher the pressure you inject at, the smaller the pores you can get the CO2 into. Okay, so let's imagine then now, so we've injected, we've gotten the pressure up to a certain amount, we've gotten CO2 into all 3 of our pores, so we've drained them partially. And then if I start reducing the pressure, what's going to happen? Well, the interfaces will just step backwards, and we will we will imbibe the wetting phase back into the pore system. Okay, and so that's the drainage and imbibition cycle. And so we'll get to this in a little bit, but this is what happens when you inject CO2 into a saline aquifer. So you initially inject the CO2 and you have a plume of carbon dioxide that moves through the that moves through the pore space. And so initially you drain the wetting phase away, but then as that plume moves away, you imbibe the wetting fluid back in. And when you do that drainage and imbibition cycle, really interesting thing happens. And it arises as a consequence of the fact that the pores in a real rock, they're not just straight capillary tubes. They're complicated. They have complicated geometry. They have differing amounts of connectivity. And so we can model the pore system in a rock as a bunch of small cylindrical capillaries, but they have a distribution of sizes and they have a distribution of neighbors that they're connected to. So let's imagine doing our drainage and imbibition experiment with this pore network now. You can imagine these are all cylinders. You can see they've got different sizes and they are connected to the exterior at different places. So now let's imagine that this is initially saturated with water, with brine. And I'm going to start injecting CO2 from the left. So I will start draining water out of this pore when I can form the CO2 water interface in it. So I have to overcome that capillary entry barrier in this pore, okay? Now, what's interesting, though, is that once so I've got CO2 into this pore. Now that CO2 can't go anywhere until I increase the pressure again, because you can see that that pore has a smaller radius, and this pore also has a smaller radius. So we'll have to crank up the pressure a little bit more to move the CO2 farther. And when we do, what happens is all of a sudden the CO2 just breaks through all the pores because we've got a large pore here, and then this pore has the same size, and then there's some more large pores over there. So we've automatically overcome the entry barriers in those pores. And so we formed this connected pathway of CO2 that goes through the pore space. Now, we haven't gotten CO2 into these pores yet because they're too small. We haven't increased the pressure enough. So let's increase the pressure enough to get the CO2 into those two pores. So you can imagine you've injected CO2 into your aquifer. You've got a plume of CO2 buoyantly migrating through it because the CO2 is less dense than water. And so once the plume was moved by, then you're going to imbibe water back into those pores. And so what's going to happen is that the water will go into the smallest pores first, because now you're decreasing the pressure of the CO2 phase. So you might be wondering, well, wait a minute, how can the water get back in there if the CO2 is blocking those pores? Well, there's some interesting phenomena that happen with film flow on the surfaces of the tubes. We can just imagine that's happening. And so if you keep reducing the CO2 pressure, it'll allow water to get into the next progressively larger set of pores. But now you'll notice something that starts happening, which is that the CO2 has been trapped in this large pore. It can't get out because the pressure hasn't been reduced enough. So it's been trapped by capillary forces. And if we keep reducing the pressure, we will not be able to get that CO2 out. It's going to be trapped. And we call that residual gas. And that's really important for understanding CO2 storage. Oh, that's one. Because it's that trapped gas that, well, as we'll see, it tends to mineralize first. And we'll talk about why that is. So here's the process I was describing. So let's imagine you're injecting your CO2 in your injection well over here on the left. And so over time, the plume will move to the structurally highest part of this aquifer. So we're looking at a vertical slice through the aquifer here. And as it does, you'll have a drainage process here initially, and then as the plume migrates away, you'll have imbibition back in there. But there'll still be some residual gas trapped behind here. And this diagram here, it's been shaded by what we call the CO2 saturation. That's the fraction of the pore volume that still has CO2. And like I said, the residual gas down here, this is really important because the residual gas exists in these little clusters of bubbles that we call ganglia, and they tend to have very high surface area. So you can see here these little ganglia just hanging out here in the pore space. The high surface area of those little bubbles means that they can react more easily because they have a higher surface area per unit volume. And so that allows them to turn into carbonate minerals or other things more rapidly. So this is an important step for the storage, permanent storage of CO2. Okay, so that's the drainage and imbibition process that gives rise to residual trapped gas, which is an important thing. Now, the other thing that the capillary forces are responsible for is retaining the CO2 up here underneath the seal. And the reason for that is that the pores in that seal are going to be much smaller than the pores in the aquifer. So if we look at these, this is, we saw this the other day, this is a thin section image of Berea sandstone. And you can see the pores are very large. They're on the order of 1 to 200 microns. The seals are typically made up of muds and mud rocks, and those typically have very small pores. And so these pores are so small that at a given pressure of the CO2 phase, the CO2 cannot go into them, so it can't leak. The size of those pores actually limits the amount of CO2 you can store in the reservoir, and we'll talk about that next. Okay. Any questions about drainage, imbibition, residual trapping? No. Okay, fantastic. Okay. A lot, not all, but a lot of sedimentary basins will have alternating layers of reservoir or aquifer and seal. This is an example of a what we call a fluvial system from the subsurface down here in South Texas. And this is a color coding of the different types of rock that have been encountered in these wells that were drilled here. The yellow stuff that we call that channel fill, that's going to be sandstone. So the stuff that was deposited within the river channel. The other one you want to pay attention to are the white intervening layers. That's going to be the mudstones that were deposited where the river channels weren't. So those are going to be your seals. And then the yellow areas are going to be your potential injection targets. So, you want to find a place where you've got a good quality injection target that's got good quality seal above it to maintain the storage capacity of your CO2. And so this actually would probably be a good injection target because you've got multiple stacked layers of reservoir quality rock, and they're capped by a big, thick seal sequence. So these are the types of things you want to look for. Okay, so let's talk about kind of the engineering aspects of how these seals actually work. Okay, so let's imagine a very simple sequence where we've got a seal rock up here. We're going to call it a shale. It's going to have very small pores, very small grains. And then we've got a sandstone below it. So large pores, large grains. So how much CO2 can we actually store in this sandstone if we have to rely on this seal to hold it back, to keep it from leaking? So really what we need to do is we have to ask, what is the maximum pressure that the CO2 can have right here at the base of the seal where it won't start leaking into the pores of the seal? Okay, so to start off, we'll make an assumption that the water phase pressure increases along a what we call hydrostatic gradient. So it's just increasing due to the weight of the water that's above it. So for typical brines that we see in the subsurface, that rate of increase is about 0.447 psi per foot. So we call that either a normal gradient or a hydrostatic gradient. All right. Now, right below the seal, so we know that the CO2 is not wetting because this is a sandstone reservoir. And so that means that it will have a higher pressure than the water phase at any given depth. And that's simply going to be equal to the capillary pressure. So we know that at this point here, the CO2 pressure is going to be larger by some amount equal to the capillary entry pressure of the largest pore in the seal. And that's going to be given to us by Washburn's equation. Okay. So that's what our boundary is going to be up there. We don't know what that pressure is, but we know that it's going to be some whatever the maximum allowable CO2 pressure is. Okay, now below the seal, the CO2 pressure also will increase with depth, but it's less dense than water, and so it will increase less rapidly. We also have to account for the compressibility of the CO2. And so the pressure, we write it as a function of depth, like this, where we're integrating the density. So the density is a function of pressure and temperature, but this just means that the first derivative of the pressure with respect to depth is just given by gravity times the local density. But the short version here is that the CO2 pressure increases as you go deeper, and it would intersect the water phase pressure at some depth. But what happens is that this reservoir rock also has a capillary entry barrier. And so for the CO2 to exist, it has to be at a pressure higher than that capillary entry barrier. So the bottom of the CO2 column is going to be defined as the point where the pressure difference between the CO2 and the water is equal to the entry pressure of the reservoir. Okay, so the maximum height of the CO2 column is going to be dictated by the entry pressure of the seal rock and the entry pressure of the reservoir rock. We call this depth here the gas-water contact because the gas doesn't exist below that, because it can't be present in the pore space. Okay, so we define the gas-water contact. There's also kind of an imaginary depth called the free water level, which is where the gas pressure would intersect the water pressure. And at that depth, the capillary pressure is 0. So that's what that is. And so what we see is that the height of your CO2 column is given by the largest pore size in the seal, the largest pore size in the reservoir, and then the local pressure and temperature, which are going to affect the density and the gradient of the CO2 phase. Okay. Any questions about that? No. All right. Let's do an example problem that hopefully will make this make a little more sense. Okay. So let's imagine that we're basically going to define this system here in terms of like depths and pore sizes and stuff. Okay. So our injection target is a sandstone. The largest pore is 10 microns in radius. And the seal has the largest pore size of 50 nanometers in radius. The top of the reservoir is 8,000 feet below surface. The average temperature is 150 degrees Fahrenheit. The brine is normally pressured. And so what we want to get is what's the expected depth of the gas-water contact. So we'll assume the rocks are cylindrical, ideal gas behavior, completely water wet, and the interfacial tension is 0.03. Okay, so that should be all the information we need. So first of all, we're going to define the entry pressures for the seal and the reservoir, because those are the capillary pressures we're going to need to figure out the thickness of this column. Okay, so we'll use Washburn's equation for this. So in the reservoir, I'll use 10 microns for my radius, and then plugging in the interfacial tension and the contact angle. I see that the entry pressure is 6,000 pascals, which is 0.87 psi. So that is the minimum pressure the CO2 phase would have to exist in the pore space of that rock. We do the same thing with the seal. We see that the entry pressure is 1.2 megapascals, which is 174 psi. So as long as the pressure of the capillary pressure at the top of the CO2 column is less than 1.2 megapascals, we won't experience leakage into the seal. Okay, so let's insert those numbers onto our diagram here. So again, this pressure difference is cannot be larger than 1.2 megapascals. And this pressure difference down here cannot be smaller than 6 kilopascals. Okay. So now we need to figure out what this difference, this distance is between the base of the seal and the gas-water contact. And the way to think about this is both the water pressure and the CO2 pressure are increasing, but their difference is actually decreasing as you get deeper. And so we need to figure out what that rate of decrease is and how far it would take us to go from 1.2 MPa to 6 kPa. Okay, that's the basic strategy here. So we know that the behavior of the CO2, we're going to use the ideal gas law for the equation of state, and that will allow us to get density as a function of pressure. And so if we start off with the ideal gas law, PV equals nRT, we can re-express this in terms of the density, because the number of moles of gas is going to be equal to the mass of the gas divided by its molar mass. And so that is equivalent to the mass divided by the volume now is equal to the density. So we can recast the ideal gas law in terms of density. And now this tells us that the density is just given by this term down here. So now we have it in terms of pressure and temperature. So we're going to simplify this. The temperature, we're assuming it's constant. And then we'll take the molecular mass or the molar mass of CO2 and the universal gas constant. And that gives us this expression here, which is valid for pressure in pascals and density in kilograms per cubic meter. Okay, so we've just plugged in all the constants there. And so the reason we need this, again, is because for a compressible fluid, the change in pressure with depth is given by the local density. And so we're going to go through that exercise here. Okay, so that's that. And so the water pressure at this depth, we're at 8,000 feet. We know that we've got a normal gradient. So we take 1 atmosphere, and then this is going to be the pressure. So that gives us 24.8 megapascals in the water phase. And we know that the CO2 pressure here is going to be the water phase pressure plus the capillary pressure that we have there. So it's going to be, cannot be larger than 26 megapascals. Okay, and then the density of the CO2, if we plug that pressure into our equation from before, it's 408 kilograms per cubic meter. All right, now, if we look at how rapidly the water phase pressure increases, we know that it increases at 10.1 kilopascals per meter. And the CO2 pressure increases, we'll assume that the density doesn't vary much between the seal and the gas-water contact. So we'll leave a constant density, 4 kilopascals per meter. And we know that at the gas-water contact, the CO2 pressure will be 6 kPa larger than the water pressure. So now we just set up an equation. So if I take some arbitrary depth, we'll call it D, below the seal, the capillary pressure will be given by this expression here, where this is the CO2 phase pressure, and this is the water phase pressure. So they're both increasing, but at different rates. So we can simplify this down, and we can see that this capillary pressure is given by this expression over here. So we need to find the value of D where the capillary pressure is equal to 6 kilopascals. And so we just plug in 6 over here. We solve for D, and we see that it's 196 meters, or about 642 feet. And so this means that we can store a maximum column of 642 feet of CO2 beneath this seal before it will start to leak. Okay. This is a really important calculation to do when you're looking at sequestration targets, because you need to know what the ultimate storage capacity of your saline aquifer is going to be. Because the problem is, if you inject too much CO2, it will leak. And that's what we want to try to avoid. And so you want to make sure you have a good handle on what your seal capacity is. When you're talking kind of in a corporate sense about the risk and doing risk analysis associated with carbon storage, seal risk is, one of the largest ones, because it can be very difficult to quantify. But at the same time, if you don't get it right, you really risk, having, loss of CO2, leakage, and that sort of thing. So you want to make sure you do your diligence. And this is why having a good friend who's a geologist or a petrophysicist is important for doing these things. Okay. Couple of things we didn't mention is that if the capillary entry pressure of your seal is high enough, it can actually be possible that the CO2 can hydraulically fracture the seal before you get leakage into the pores. So you have to be aware of what your fracturing pressure is as well. And also you want to be careful, because CO2, if it finds an abandoned oil and gas well or something like that, it can leak back to the surface through that. It can leak around the injection well as well. So you need to make sure that you've good wellbore integrity associated with your CO2 storage. I have a friend who works for an oil and gas company that does a lot of carbon storage, and he was telling me that the largest cost when they start operating an asset for carbon storage, the largest cost is remediating the old wells that are in there, because those are their biggest risk for leakage, and it takes a lot of money. Particularly if you've got an old field that has like 100 wells in it, you think about pulling the casing and re-cementing all those, like that's, tens of millions of dollars, if not more. So that's a big deal. Okay, and this is just an illustration of what these leakage pathways can be. They can be along faults, they can be along old wells, you can have diffusive leakage, so you have to be very careful about where you store your CO2. Okay, so that was our capillary pressure lecture for the semester. Any questions about any of them? No. Fantastic. So when we do our project at the end of this unit, I'll be asking you guys to research a CO2 storage project and talk about any problems they've had with it. And seal risk is definitely one that you see come up in already the experience we've had with field operations with CO2 storage. So make sure you keep a lookout for that. Okay, I think that's a good stopping point for today. We'll come back and probably wrap up our carbon storage on what day is next? Wednesday. But I hope you all enjoy the rest of your Monday afternoon, and I'll see you then.